All right, my friends, welcome back. Hope you had a good weekend. Today we're going to finish up quickly on epoxides and then move on to alkene chemistry. But just to remind you where we've been in this chapter, our theme has been that OH minus is generally not a good leaving group. So we have to do things to the alcohol in order to prepare for substitution or elimination reactions. The easiest, of course, is to protonate the alcohol, but if you do that, you're going to get a carbocationic intermediate, and we talked last time a lot about the potential for 1,2 hydride or 1,2 alkyl shifts, whereby a secondary carbocation can rearrange to become a more stable tertiary carbocation. And we learned to draw the elimination products that would come from the unrearranged carbocation and the rearranged one. You might expect, because this makes a mixture of products, this isn't exactly synthetically useful, but the concept of carbocation rearrangement is important in biology, and we talked about the synthesis of steroids with many examples of 1,2 hydride and methyl shifts. On the substitution side, let's see. No. Let's still stay on the elimination side. We introduced a new reagent, POCl3, which converts the alcohol into the olefin or alkene without any carbocationic intermediate and therefore no rearrangement. We didn't worry about the mechanism for this. It's in your text. I'm not going to ask you questions about it. You may just need to memorize that there is no carbocation rearrangement because there's no carbocation intermediate here. I don't have a really good reason why you don't have a carbocation intermediate here. Yeah?
So on the above example, the product in red, can that still happen even though it can shift?
Yeah, can we get the red one, which only comes from the non-rearranged product, even though we can go here? Yeah, I don't know. The fact is you'd have to go in the lab and see. You might suspect the most stable alkene to be your major product no matter what, but you wouldn't be surprised to see some of these other ones. So case-by-case basis, I just want you to anticipate the possibilities. Yeah?
Can you have carbocation rearrangement that maintains stability? So it's like a secondary to secondary.
Yeah, can you have carbocation rearrangement that maintains stability like secondary to secondary? Let's see, was it there? Nope, probably here. Yes, we did that a ton in the steroid synthesis, where, for example, here we exchanged a tertiary carbocation for another one, and that kind of thing can happen. I don't really care about you predicting that. I'll only expect you to deal with carbocation rearrangements, at least in these types of reactions that take a secondary carbocation and turn it into a more stable tertiary one. The other stuff's possible, and you may get to stuff at some point in 352 where that becomes necessary, but for now we'll stick to that situation. All right, we talked about substitution reactions. Same idea here. We have a couple of different reagents, either PBr3 or SOCl2 and pyridine, that convert the alcohol into an alkyl halide with inversion of configuration because it's an SN2 reaction. And once you've done that, you can add any nucleophile you want and do alkyl halide chemistry, and you get another inversion. And so this synthetic pathway would give us the cyanide up. If we wanted to turn the OH into a good leaving group without messing with the carbon, we use Paratoluene sulfonyl chloride. The reaction is oxygen as a nucleophile attacks the TSCl reagent, and you make the tosylate. Structure of that is shown in your text and in the notes from last time. This is a good leaving group, which can again be displaced via SN2 to give this product. But the key is this pathway on top only has one stereochemical inversion instead of two. So there are some unique stereochemical outcomes, and I love to ask synthesis questions where I show you this reagent, or sorry, this product or that product, and a starting material of a certain stereochemistry, and you have to choose the correct path that gets there. One will give you the correct stereochemistry, the other will not, and so you need to master that. Finally, we talked about epoxides, and we just barely got to talking about them. So an epoxide is a three-membered ring containing oxygen, and it's electrophilic at the carbons that are bonded to oxygen. In this case, I've chosen an epoxide that's symmetrical, so carbon 1 equals carbon 2. So we're not worried yet about which one gets attacked. We will be in a couple of minutes. But a nucleophile can attack in SN2 fashion, and one of the carbon-oxygen bonds breaks. Presumably the nucleophile is attacking the carbon-oxygen sigma star. The thing that leaves is a negatively charged oxygen. And we talked about how before that's not a great leaving group, but the thing that pays for it is the fact that you're relieving ring strain associated with this three-membered ring. All right, and so relief of that ring strain drives the reaction forward. Once you get this negatively charged oxygen, usually in the aqueous workup after the reaction, we can pick up a proton from water or solvent, and that gives us this substitution pattern where you have a nucleophile and an OH group on adjacent carbons. This sort of 1-2 nucleophile OH substitution pattern. If you see that in a product, you could think, I could have made that from an epoxide. All right, so couple of things to be aware of with epoxides. The SN2 nature of the reaction means there are stereochemical consequences. Of course, here we don't make any stereocenters, so you can't tell that the nucleophile came in from the opposite side, but we can easily make situations where stereochemistry is important. So I will draw this epoxide with the oxygens coming out towards us, with the carbon-oxygen bonds coming out toward us. And in the front, oh, that's not great, we'll have methyl groups. And in the back, we'll have hydrogens. By the way, you can draw epoxides any way you want as long as the stereochemistry is correct. These two drawings are interchangeable. They're the same thing. You get the one on the right just by tipping that oxygen down into the plane of the page, right? Okay, so notice that we'll just, is this epoxide chiral? Nope, why not? Plane of symmetry, good. So we might call this a meso epoxide. What about this one? Or alternatively, you can draw it like this. Is that chiral? Yes, two stereocenters, no plane of symmetry. Yeah, so this is a meso epoxide. This is one of the enantiomers, and we could draw the other enantiomer, and it would look like this. All right, that's a fun little review of stereochemistry. Now let's open up the epoxide, and let's do so with hydroxide and water as the solvent. Notice that in our meso compound, we'll call these atoms A and B. In our meso epoxide, atoms A and B are identical, so we're not going to worry about which one gets attacked. Let's draw what would happen if hydroxide attacked at carbon A. So here's your nucleophile. This one comes in from below and breaks the carbon-oxygen bond so that after the reaction, We have negatively charged oxygen there. Stereocenter B remains unchanged. And we'll put the methyl group here in the plane of the page. Methyl group here stays in the plane of the page. The proton is now up, and the OH group is now down. We get inversion of stereochemical configuration at A. To see that the oxygen was up, it left, and the nucleophile came in from below. Yes-ish? No? All right, what if we erased the hydrogens? Would it make more sense then? Okay, the hydrogens extraneous detail, what you're seeing is the umbrella inverting of the hydrogen. When the new oxygen comes in, the hydrogen, which used to be pointed this way, has to flip up as the leaving group leaves. That's inversion of stereochemistry. So we can erase it if that would help you see it better. Same thing either way. All right, and then this oxygen is going to pick up a proton afterwards to give us the following product. On one carbon, we have an OH that's up. On another carbon, we have an OH that's down. Okay, is this product chiral? Yes or no? Pick one. Come on, commit. Yes, okay, it is chiral. You can tell that because there's no plane of symmetry. This OH is up, whereas that OH is down. There's no symmetry there, and it's not the same as its mirror image. All right, so here's a tough thing. We started out with a not chiral meso compound, but we got a chiral product. You can't get chirality ex nihilo, so what does that mean? If we form one enantiomer, we have to also form the other in equal amounts. Where does that other enantiomer come from? Attacking B, right? If you attack B, let's draw this. We got this one from attack of A. If we attack at B, then what we're going to get is the OH here and an OH there. We're going to get exactly the enantiomer of what we expected. Again, if we attack at B, then the OH group is going to be down at B. So we get from the meso compound in this reaction, we get two pairs of enantiomers. All right, so we've kept all the stereochemistry rules, but I like to ask questions on exams where I show you a product like this, and you have to figure out what the appropriate epoxide starting material was. And you might be tempted to say this one or that one. The only difference is stereochemistry. You've got to be able to follow the stereochemical implications of this reaction. We can do the same thing with the chiral starting material, the chiral epoxide. Again, though this molecule doesn't have a plane of symmetry, it does have what we're going to call a C2 axis of symmetry. That means if I rotate around the axis that I've drawn by 180 degrees, carbon A comes into the place of carbon B, and it looks exactly the same. So again, in this example, carbon A equals carbon B just by symmetry. Ooh, cool, we've got the Eye of Sauron there or something. I realize that Lord of the Rings references appeal to a narrower audience than Star Wars references, but what are you going to do? Let's see. So these two are pairs of enantiomers. Let's show what happens if we have hydroxide attack at carbon A. And maybe for our purposes, we'll just draw this happening from the same perspective as we did previously. So we're going to attack from behind. The negatively charged oxygen leaves. Methyl group stays in the same place. OH group came in from below. Then that negatively charged oxygen is going to pick up a proton from water. And then our product will look like this. And we could stop there. I mean, it's fine. But it might be nice to try to examine whether or not this molecule is chiral. And to do so, we're going to rotate around this carbon-carbon bond. We're going to tip the oxygen, the OH here that's up, back into the plane of the page and then down. So that's rotation by about 120 degrees. That is going to swing this proton up and bring this methyl group into the plane of the page to give us, yikes, this conformation of the molecule, which is a little bit easier to tell. Sorry about the mess. A little bit easier to tell that it's, dang it, chiral. I mean, not chiral. A little bit easier to tell what kind of compound this is. There's the plane of symmetry. So we've made a meso, not chiral, 1,2-diol. So interestingly, it's kind of weird. You take the meso epoxide, you get 2 enantiomers that are chiral. You take the chiral epoxide, and you get a meso-diol. So the point is just that stereochemistry of the starting material shows up in the or influences rather the stereochemistry of the product. Now, because this is a meso compound, it's obvious that it's not chiral, so I'm not going to go back and show what would happen if you attacked B. I'm also not going to go back and show what would happen if you attacked A or B in the other enantiomer. If you'd like to, you can do that and convince yourself that all 4 of those pathways, A and B in this enantiomer, A and B in this enantiomer, lead to the same meso compound as the inevitable product. Yeah?
These meso and enantiomer rules only apply if the reagent is OH minus group.
Yeah, exactly. So the rules here only apply if your nucleophile is an OH group, because then you've got a 1,2-diol. In the sense for like chiral versus not and meso versus 2 enantiomers. But the stereochemical principles are true no matter what. So any nucleophile that we might come up with is going to attack the epoxide from behind. This is an example of the SN2 reaction is an example of stereospecificity. That means that the stereochemistry of the starting material has to influence the stereochemistry of the product because of mechanism. So the relationship between the 2 starting materials is diastereomers. And notice how the relationship between the 2 products is also diastereomers. That is, if I switch the starting material from the mesodiastereomer to the chiral epoxide, then I will switch the products from here, the chiral 1,2-diol to the meso 1,2-diol. Okay, so there's I don't think any rules to memorize there other than can you follow through the consequences of the SN2 reaction? Do you know what it means to have stereochemistry switch? Okay, now we need to deal with, that's the stereochemical issues of epoxides. We need to deal with regioselectivity of epoxide opening. Regioselectivity means, whoa, that's not how we spell selectivity. Regioselectivity means selectivity among regioisomers or constitutional isomers. We're going to be dealing with different connectivity patterns. Regioselectivity of epoxide opening. All right, so let me give you an example of an epoxide. This is an epoxide that's attached to two of the carbons of the six-membered ring, and one of the carbons has a methyl group on it. We'll call this A and B. You have two possibilities here. If you attack at A with your nucleophile, you could get the following product. Methyl group would be up, nucleophile would be down, and then you'd have an OH here. I'm showing you the product you get after aqueous workup, after you protonate the negatively charged oxygen leaving group. Notice that the nucleophile and the OH group are trans relative to the ring. Opening up of the epoxide gives you this trans relationship. Instead, if we attack at B, we're going to get the nucleophile here, the oxygen of the epoxide here, and the methyl group here. Okay, and those products are not stereoisomers. Notice that in the product above, the nucleophile came in on carbon A, whereas in the product below, the nucleophile came in on carbon B. So these two are regioisomers. Now the question is there a preference for one versus the other, or do we just always get a mixture? And the answer is no, you can select for one versus the other depending on the conditions that you use. So strong nucleophiles under basic conditions prefer attacking at B, which we're going to call the less substituted carbon. Okay, so let me give you an example. We have to choose a nucleophile that's different from oxygen so we can really see this. Let's just use the following nucleophile. This is an acetylide anion, and this is a strong nucleophile, so we can have it attack carbon B from below, and after aqueous after aqueous workup, we would see that that acetylide anion came in from below on carbon B, so the OH ends up pointing upward, on carbon A. All right, do you see how the nucleophile here attacked the less substituted carbon? The reason for that is that the mechanism is SN2, and therefore sterics matter. And by SN2, I'm going to say like conventional SN2. By that I mean, like, if you remember our plot where we had like nucleophile attacking and leaving group leaves, and we said that the SN2 pathway was straight there to substitution products. Here's our starting materials. This was the SN2 pathway. Transition state was right about there. So the fact is that when you have a straight up SN2 reaction, the sterics matter, and so it's preferred to attack at the secondary carbon instead of the tertiary one. Makes sense based on things you've learned about substitution reactions. Yeah?
What do you mean by like under basic conditions?
Basic conditions where things would be deprotonated, I mean negatively charged conditions. So, for example, this negatively charged acetylide comes from acetylene, which has a pKa of 25. So we're talking about using nucleophiles whose pKa's are high. Yeah. Or using negatively charged nucleophiles, but I mean under basic conditions, I mean there's no hydronium, not much hydronium present, so that the thing that leaves is a negatively charged oxygen. Okay? Yes?
Sorry, just to clarify, the B is considered a secondary hydrogen that is attached is not in the carbon group, so it's considered secondary on here.
B is a secondary, well, ooh, that was wrong. Before the epoxide attacks, you could call this a secondary carbon because it's attached to it's got two carbons bonded to it. Yep. Okay. So what I mean by basic conditions is these are conditions where the nucleophile attacks the neutral epoxide and the leaving group is the negatively charged oxygen, and then only after that do you do aqueous workup and protonate the alcohol. Okay. Now, the second option is opening epoxides under acidic conditions. So how might this happen? Let's take the same epoxide and let's open it up with HCl. All right. So, and it's okay if you want to think of this as happening with HCl. Remember, when you buy HCl at the stockroom, what you're really buying is this. But if you use a strong acid, the thing that's going to happen first is that the oxygen of the epoxide, which has lone pairs on it, is going to deprotonate the acid. And that's going to give you this oxonium ion intermediate. Okay? The reason this can happen, by the way, is if you compare the pKa of HCl, which is like -9, versus the pKa of the protonated epoxide, positively charged oxygens with protons tend to have pKa's around -2. It would be favorable to go from HCl to this protonated epoxide. Okay? Now, I told you before that the key deal with epoxides is the negatively charged oxygen is a bad leaving group, but if you relieve ring strain by opening it up, that's fine. What do you suppose happens to the epoxide when I protonate the oxygen? Does it become more or less reactive? Because you got an even better leaving group now, right? So what this does, in terms of our reaction mechanism, we talked about how in blue we have sort of the pure SN2 reaction. But in the case of this epoxide, once we protonate the oxygen, it becomes an even better leaving group. And that's actually going to pull our transition state here a little bit towards leaving group leaving. Okay, because we got a better leaving group, so our transition state's going to move to a place that's maybe about the same in nucleophile attacking, maybe even a little less, but with the leaving group having left more. Okay, so if this is our new transition state, let's draw the new pathway. Okay. So what we mean by this is that the pathway taken once you protonate the epoxide is that the leaving group starts to leave a lot before the nucleophile even comes in. And then at that point, the leaving group leaves completely as the nucleophile comes in. So let's try to draw what this transition state might look like for the protonated epoxide. We said the leaving group is going to leave quite a bit even before the nucleophile comes in. So I've got two carbons here. I've got A and B. And if the leaving group leaves before the nucleophile comes in, that's going to build up some positive charge on the carbon it leaves. Now, which of those two carbons is best able to tolerate a positive charge? A, the more substituted carbon A, better stabilizes a partial positive charge. And the reason for that is what we learned about carbocation stability earlier in the semester. So our transition state should involve the bond between A and B getting longer and a buildup of partial positive charge on the more substituted carbon where it's more stable. And it should involve a substantial amount of rehybridization of carbon A. If the leaving group starts to leave, if it left completely, we'd have a full carbocation here, and that would be trigonal planar. But at this point, the geometry around A is less tetrahedral and starting to flatten out. Okay, that's what our transition state looks like in terms of the epoxide. Now, as I said, the nucleophile is going to wait to come in until that leaving group starts leaving. So I'm going to show this bond that's going to form between chloro and carbon A as being quite a bit longer. Okay? So the fact that the transition state involves the leaving group leaving means it's going to leave mostly from the carbon that best tolerates the positive charge. That will then be the reactive carbon that the nucleophile will attack. Right? Now, it's still going to attack from behind because we don't have a full-on carbocationic intermediate. This oxygen from the epoxide is still sort of blocking the top face of the molecule. So the nucleophile, as I said, is still going to come in from behind, but it's going to attack carbon A because that's where the buildup of the positive charge is in the transition state. Okay? So this is our product where the nucleophile has attacked carbon A. Now, people usually ask, what about what you said in chapter 7 and 8 about how there is no SN2 reaction at a tertiary carbon? This is one of those pesky exceptions, and the reason that it works is because this is not a pure SN2 reaction. A pure SN2 reaction involves the nucleophile coming in at about the same extent as the leaving group is leaving. Epoxide opening is still SN2 because it's concerted, still concerted, but it is SN1-like. What do we mean by that? Well, there's a greater amount of leaving group leaving in the transition state. As I said, carbon A is going to flatten out a bit. It's going to become less tetrahedral, but not completely flattened out. The oxygen still blocks the top face, so the nucleophile still has to come in from behind. But carbon A is less sterically hindered now as those alkyl groups start to flatten out as the carbon rehybridizes. All right, so regioselectivity of epoxide opening. If you open them under acidic conditions, we attack at the less substituted carbon, which we've called A here. Okay, questions about that? Yeah.
This might be off track. I'm trying to balance out the charges before and during the transition state.
Yeah.
So before the negative cancels out the positive, and so there's net charge of 0 for the whole system.
Yeah.
But during the transition state, is
The
CL not a partial negative?
Yeah, I suppose during the transition state, Cl would go from being full negative to maybe partial negative to the extent that we form this bond.
Then what would share that partial negative?
The partial positive on the oxygen and on the carbon. We start out with neutral starting materials, so the overall charge has to be neutral. We're just changing who has most of it.
Okay, so partial positive on the carbon and the oxygen.
Yep.
Partial negative on the chlorine.
And if you added up the partial positive, it would exactly cancel out this partial negative.
Okay.
Yep. You can actually do quantum mechanical calculations that tell you about what charge is on each atom. It's kind of tricky and it depends, but on the method that you use. But yeah. Yeah.
I'm still tripped up on how the carbon A and oxygen bond gets longer. Is it getting stronger or weaker?
It's getting weaker. The bond between A and this oxygen gets weaker because that oxygen starts to leave.
So because carbon A can handle the positive charge more, then the bond gets weaker.
Exactly. Carbon A can handle the positive charge. If the leaving group leaves, it starts to relieve some ring strain, so you can get there. Okay. Others? Yes.
I think under that you meant to say it affected the more substituted, right under number 2.
Yes, I did. Whoops. Thank you for catching that. Excuse me. Others? All right, so that's it for epoxides. There's nothing more mechanistically I need to tell you, but you should practice that quite a bit because it's a stereochemical minefield. You've got stereochemical issues, you've got regioselectivity issues. Make sure you're able to do all of those. Okay, yeah.
Before we move on to chapter 10, were you able to push back when the test is?
Yeah, so I haven't done that with the testing center, but you're not going to have a test at the scheduled time. I suppose we can do that right now.
Just give us all that also you wouldn't have to
Magic, yeah. Yeah, I should do this offline, but while we're thinking about it, let's just get it done.
you post a study guide too while you're at it.
I have posted study guides 9 and 10.
Oh,
I wasn't sure how, I wasn't,
study guide with the keynotes.
yeah, I'm not sure how far we're going to get. So first we need to choose an exam date. Okay, I'll do that after class. It's asking me to find Duo and I don't want to. It's irritating. Yeah. Okay. Yeah, so I'm sorry for the disorganization. I will email you as soon as I schedule that test date. As I said, I think we will push it back a week. Now, that's going to provide some relief in the short term. It doesn't change the end date of the semester, so that's going to result in some increased pressure at the end. You can have stress now and stress later, slightly less stress now, slightly more stress later. It's all the same amount of stress, so I'm sorry.
Lost their extreme.
Yes. Okay. Chapter 10 is long because what they did for this chapter, in previous editions of the text, there was a chapter about alkenes and then a chapter about alkynes. And the alkyne reactions there were tons of them, but they weren't that important. And so I thought they would maybe eliminate some of them from the book. Instead, they just shoved them all into chapter 10 and then added another chapter to the text. So I don't particularly like that. So what we're going to do is talk about alkenes. We're going to talk about what's called electrophilic addition to alkenes. We're going to use the alkene pi bond as a nucleophile. Any of the reactions we talk about for alkenes could also be done for alkynes, and it's not that hard, but I don't care enough to worry about them. We will, however, do the one thing in chapter 10 on alkynes that's useful, and that is using them in synthesis. So the study guide for chapter 10 has you just read only specific parts of chapter 10 that we're going to cover. This is going to be the first of many times in your OChem experience where you're going to be introduced to 4 or 5 new reactions. And if you think about them as separate and disconnected, you have to add separate filing drawers in your cabinets in your brain for this kind of stuff. But actually, if you see them as all manifestations of the same basic reactivity, it may be a little bit easier to work through this. So let's talk about alkenes. I'm trying to choose the best example to get started. All right, I have to choose my example carefully because I want there to be issues of regioselectivity and of stereoselectivity. D here, as you look, is not on the periodic table. D stands for deuterium, an isotope of hydrogen that has a neutron, and therefore deuterium, deut stands for 2, so it weighs twice as much as hydrogen. Organic chemists use this as a convenient label. It has basically the same chemistry as hydrogen. I can't write while talking. Convenient label. It won't change the chemistry, but you can tell the difference between hydrogen and deuterium through experiments that we'll talk about later. Okay, any questions on what deuterium is? When you see it, don't panic. Just say, okay, isotope of hydrogen. It's the chemical way of shading in one particular hydrogen. Okay, we can't paint hydrogen atoms, unfortunately, but we can add neutrons to them, and then we can see them. All right. So in chapter 10, we're going to use the alkene as a nucleophile. So you tell me, if the alkene is a nucleophile, what is the highest occupied molecular orbital? Pi bond, the carbon-carbon pi bond. And if you were to draw what that orbital looks like, we would have a lobe of electron density above the plane of the page and below the plane of the page, with the page itself being a node. And what we would expect is that the alkene can attack with its top face or its bottom face. Those two faces are equivalent. So just like with epoxides, when we had to think, do you attack carbon A versus B, we're going to have to also think about, do we attack from the top or the bottom, and consider those options. All right, so now we can bring in any number of electrophiles. And the reactions that we talk about in Chapter 10 will all have this same basic alkene starting material, but depending on the electrophile, we're going to have different outcomes. So let's do a reaction that's called hydrohalogenation. We're going to use a halide acid like HBr or HCl. Your text will call this hydrohalogenation because you put TION on the end of anything and it becomes a process, right? Let's see. So we're going to show the electrons in the pi bond attacking the hydrogen of HBr to break the hydrogen bromide bond. Okay? Now, pi electrons that used to be shared evenly between, we'll call them carbons A and B, now are going to only be shared between one of those two carbons and the hydrogen. One of those two carbons is going to get the CH bond, and the other is going to get a positive charge. Now, tell me which one gets the positive charge. A does, because more substituted. Remember, deuterium is just like hydrogen, hasn't got any more electrons than hydrogen does. So B is still a secondary carbon, A is a tertiary carbon, and B should get the positive charge. Why? I'm sorry, A should get the, man, I just worry about myself sometimes. A should get the positive charge. Why? Because it's more substituted. So we get the more stable, more substituted carbocation. Again, carbocation stability like you learned in chapters 7 and 8. So that's no surprise. Now you might be tempted to memorize, okay, so when I add an acid to an alkene, if the alkene has a difference in substitution between the two carbons, the hydrogen should go on the not more substituted carbon. But all of that falls out if you understand HOMO attacking LUMO, forming a new CH bond. You have to have a carbocation intermediate, and you should put it on the more substituted carbon because that's more stable. So the Y will give you the mechanism in this case. Now, we haven't talked about carbon B yet. I already have a deuterium on that carbon, and now I'm going to have a hydrogen on that carbon. Should the hydrogen be up or down? Who knows? So if you attack from the top face, you would have, if you attack hydrogen from the top face, you would have hydrogen be up. But now B is a stereocenter, and our starting materials were not chiral. So we have to get the other stereochemical configuration as well. And we get that from the bottom face of the alkene attacking the hydrogen. So the intermediate on the left is top face attack. The intermediate on the right is bottom face attack. Why do these have to be formed in equal amounts? Go ahead. Do you not know? That's okay. They have to be formed in equal amounts because they're enantiomers. Good. What is it about the starting material that makes that have to happen? Go ahead. Yeah, symmetrical. The top face is the same as the bottom face here, right? So we have to get both. Okay. So I believe that early on when we learned about HOMO and LUMO, I showed you an example of this kind of reaction. We made a carbocation, and then bromine magically turned to chlorine, and then, no, I'm very sorry. So Br minus was the leaving group in our first reaction. Now, Br minus is the nucleophile. And now the carbocation is our electrophile. What is the LUMO of the electrophile? Well, the HOMO is the lone pair on Br, sure. Has to be lone pair. The LUMO is the empty p orbital on carbon A. Carbon A is positively charged, sp2 hybridized, trigonal planar, and therefore we must have an empty p orbital on carbon A. And carbon A is going to be flat, so we're going to have, oops, that's not what we wanted. We're going to have LUMO both above and below the plane of the carbocation. All right, so HOMO attacks LUMO, my nucleophile should attack the positive charge, right? Okay, and you would predict that the nucleophile has to attack from above or below. Now, let me just ask you this. Does the nucleophile have to attack carbon A from above or below to an equal extent? No, because B is a stereocenter and the faces are no longer identical. Right? No, it had to do with because of the deuterium. Now, in size, hydrogen and deuterium are basically the same. So there's not a huge amount of difference between the top face and the bottom face here. But the moral, why am I having a hard time saying that word? The moral of the story is if your carbocation has a stereocenter in it, the two faces of the positive of the p orbital are not identical, and you can have a preference for attacking one versus the other. In this case, that preference is minimal. So we would go ahead and draw from the top face attack intermediate BR having come in from above. We would also need to draw BR having come in from below. Okay, and then from the second carbocation, where deuterium is up, we would need to show the same types of products, BR having come in from above. And then also BR having attacked the carbocation from below.
Didn't you just say that you should have a preference?
You can have a preference.
Okay.
It would be difficult to predict in this case.
Okay, like if it was a methyl instead of a deuterium.
Yeah, if it was something larger, you could prefer one versus the other.
Would it be anti to the larger group?
Well, yeah, you would think so. And we'll deal with an example of that in a minute. These are going to be our products. Okay, and I want to talk about the relationship between these products. You're going to need to look at the stereocenters that we've made in A and B for each of these products. So, and I'm going to number them just to make things easier. 1, 2, 3, and 4. What is the relationship in terms of stereochemistry between 1 and 2? Are they? What are they? Diastereomers. You can tell that because one stereocenter B stays the same, the other switches. If they're not enantiomers, they have to be diastereomers. So The relationship here is diastereomers. And this is why I was saying they don't have to form in the same amount, because diastereomers have different chemical and physical properties. So you could favor one versus the other. We will have a new way of talking about these diastereomers. Let's just label the things that we added to the alkene. We added hydrogen and we added Br. Up top, we have what I'm going to call the Syn Diastereomer, because the things that we added to the alkene added to the same face of the alkene. On the bottom, we're going to have the anti-diastereomer, and we're going to call it anti because the Br and the H, which we added to the alkene, added to opposite faces of the original alkene. Okay. Yeah, so if two products are diastereomers, they do not have to form in equal amounts. You could expect one to be favored over the other. It will depend on what the groups are. If we had something other than deuterium here, something that was large, it may make sense for one of the products to dominate over the others. Now, what's the relationship between 3 and 4? They are also diastereomers. You can tell that because here the stereocenter A changes, but B does not. Using these words, which is the Syn diastereomer and which is the anti-diastereomer? 3 is what?
Oh, wait, no.
Okay, look at what we added to the alkene. If they're on opposite sides, opposite faces of the original alkene, then we will call this anti. And the one where they are on the same face of the original alkene, we will call syn. Okay. Syn for same, synonym kind of thing. Okay. What's the relationship between 1 and 3? Okay, check the stereocenters. Enantiomers will be opposite at each and every stereocenter. Diastereomers will be opposite at one, but not all, if there are stereocenters. Okay, so those are diastereomers as well. And then these are diastereomers as well, which are, I can't spell that fast. I guess I've already spelled it. Oh, I changed color. That's lame. Okay, so who are the enantiomers? 2 and 3. The 2 anti are enantiomers of each other. And then 1 and 4 are also enantiomers of each other. Okay? So in this reaction, we don't expect there to be a large preference for syn versus anti. Mechanistically, we can get both. All right? And of course, because the faces of the alkene are identical, we have to get both pairs of enantiomers. So notice that in this reaction, because I start with a non-chiral planar starting material, and because my intermediate is a planar carbocation, the 2 stereocenters I have to make in both varieties. 2 stereocenters, 2 possible configurations, 4 products. Right? So that's hydrohalogenation. Questions you want to ask? Yeah.
So the 2 that we made originally, do you still call those products, or are those just
The carbocations, we'll call them intermediates.
Okay. Did you see that those were produced like in equal proportions?
They have to be produced in equal proportions because they're enantiomers of each other.
Okay.
Yeah. and because the starting material was planar and the top face was the same as the bottom face. Yeah?
Will the enantiomers be made in equal quantities?
The enantiomers have to be made in equal amounts. Diastereomers don't. So we could find that we would have to form 3 and 2 in equal amounts. We would have to form 1 and 4 in equal amounts. If we group the anti-diastereomers versus the Syn Diastereomers, they don't have to be formed in equal amounts. Okay, what else? Shoot. Don't you hate it with these 2-hour classes? The professor can drone on and on past 50 minutes. I got in trouble the first time we went to COVID because I found all of a sudden my lectures could be a little bit longer than 50 minutes, and I heard about it in the student review. So I apologize. Let's just go ahead and take a break here. We will pause and start up again in a minute.